Today's topic is linear variable differential transformer. So that comes under the subject transducer engineering, the subject name, and so the subject code is OIC 751. So LVDT comes under the unit number 4, variable inductance and variable capacitance transducers. So what could be the outcome is that analyze the variable inductance and variable capacitance transducer that comes under the K3 level, analyze level. So MPDT is linear variable differential transformer or a transducer. So as the name itself suggested that it is a transformer. It is a transformer. So it is not a transformer, it is a transducer. It is actually a transducer. So what is a transducer? So transducer uh, will deduct what is happening there, and it will convert one physical quantity to the other form, or its equivalent electrical quantity. So one form of energy will be converted to its equivalent electrical quantity. Mechanical form will be converted to the electrical quantity. Yes, and let's see the what is LVDT in detail. Okay. So it is categorized as an inductive transducer, which is used to measure the speed or position of an object. So generally, most inductive sensors works on the principle of transformer. As you all aware, it works on the principle of mutual induction. So LVDT is an electromechanical type inductive transducer that converts rectilinear displacement into an AC equivalent electrical signal. So what is a transducer? It converts one form of energy to the other form. So what is happening here is it converts the displacement to its equivalent AC electrical signal. Since LVDT, that is linear variable differential transducer, is a secondary type of transducer, hence physical quantities such as force, weight, tension, pressure, etc. are first converted into its displacement by a primary transducer, and then LVDT is used to measure it in terms of corresponding electrical signal. So what is happening here? Let's see this. Since this LVDT is an AC controlled device, so there is no electronic component involved in this. So it is most widely used inductive sensor due to its high accuracy level. So its electrical output is obtained because of the difference of the secondary voltage. Hence, it is called a differential transformer. Yes. So as it is mentioned here in the figure, so S1 represents your secondary winding, and P represents the primary winding, and S2 represents the secondary winding. So there is a soft iron core placed at the center, and there it is being attached with an arm. So that arm will represents the displacement in the horizontal displacement. Yes. So is hydrogen annealing is done on the iron core. So where is the iron core present here? It is at the center, soft iron core, right? It is used to reduce the harmonics and residual voltage of the core, and thus provides the high sensitivity. So a very minute change can also be detected using this LVDT. The movable core also is laminated in order to reduce the eddy current losses. As you all aware, what is eddy current loss, right? So displacement to be measured is attached to its movable soft ion. So the LVDT is placed inside the stainless steel housing because it will provide electrostatic and electromagnetic shielding. So it will be explained here. Yes. So it is actually depends upon the three cases. So the first, the working principle of LVDT is based upon the uh, mutual induction principle. So here E in, E1, E2 and E out. Here these all represents the fluxes produced. Yes. So when an AC excitation of 5 to 15 voltage at a frequency of 50 to 400 hertz is applied to the primary winding. So as you all know, I think you are all aware where is primary, where is secondary. So an important, very important point is that here the secondary winding S1 and S2 both are connected in the series combination. Yeah. Yes. This magnetic field induces a mutual current in secondary winding. So this is happening with the help of the secondary winding S1 and S2. Yes, since both the secondary windings are connected in series, I have already mentioned this, right? So the net output will be the differences of both induced voltages, that is E1 and E2 in secondary winding. Hence, differential output of the LVDT will be, so what could be the differential voltage? So obviously that output is represented here as E naught, and the difference between those two inputs, that is E1 and E2, is mentioned as the differential output of the LVDT. Yes, E naught is equal to E1 minus E2. So now according to the position of the core, that is the soft iron core, no, we have seen in the first figure, right? So according to the position of the core, there are three cases that arises here. So the first one, when the core is moved towards the S1, that is maximum to the maximum of the left side. So when the core of LVDT moves towards the secondary winding S1, so in this case, the flux linkage with the S1 will be more compared to that of the S2. So what will be happening here? This means the EMF induced in the S1 will be more than that of the induced EMF in the S2. Hence, E1 will be more that of the E2. And then the net differential output voltage will be E0 is equal to E1 minus E2. That will be positive. This means that the output voltage E0 will be in phase with the primary voltage. So the E0 will be in phase with the primary voltage. Yes. So we'll move on to the next case. So case 2, when the core is at the null position. So what is the null position here? The null position is when the core is at the null position, the flux link, what happens to the flux linkage? The flux linkage with both the secondary winding will be same. So what happens to the induced EMF here? So E1 will be minus 2 that of your E2, right? So this represents the null position. So obviously what will be the output here? 0. So it shows that no displacement of the core. So that is what is happening in the case 2 when the core is at the null position. So next this is the exact diagram for this description. So observe this figure. So E out is equal to E1 minus E2, right? So what is happening here? Your core is at the center position. So what happens? Your flux produced at the E1 will and the flux produced at the E2 will be cancelled each other. So the flux produced at the EMF, that is secondary winding 1 is 1 and secondary winding 2 is 1. So 1 minus 1 is equal to 0. So that represents the null voltage. Yeah. So next is the case 3, when the core moves towards the S2, that is first condition, that is maximum to the left. Second case is the null position, and the third case is the when the core moves towards the S2, that is to the maximum right. So what is happening here? When you observe the figure, when you observe the diagram, so what is happening here? Your core is moved to the maximum right. It is not at the center, it is not at the left, it is moved toward the most maximum right. So when the core of LVDT moves toward secondary winding S2, then in this case, the flux linkage, what happens to the flux linkage here? When compared to that of your S1, S2 will be more. Yeah, it means that EMF induced in the S2 will be more than that of the EMF induced in the S1. So hence, what happens to the E2? E2 will be greater than that of your E1, right? So that the net differential voltage, output voltage will be E naught is equal to, what is the voltage? Differential voltage will be E naught equal to E1 minus E2. So E1, so 0 minus of 1. So this could be the value of negative. So it means that the output voltage be E naught will be in phase opposition, that is 180-degree out of phase with the primary voltage. Yes. Yes. So from all these three cases, we have the following three conclusions here. The direction of the movement of an object can be identified with the help of the differential output of the LVDT. So similarly, if the output voltage E naught is positive, then this means that an object is moving towards the left from the null position. So similarly, if the output voltage E naught is negative, what happens there? Then this means that the object is moving towards the right of the null position. One to the extreme right, one to the extreme left, one at the center, that is the null position. So what's happening here? So corresponding to the both the cases, whether the core is moving either to the left or right or to the null position, the output voltage will be increased linearly up to 5 mm of the null position. And after 5 mm, output E naught will be non-linear, right? So this is the graph variation of output with respect to its position, and that has been represented in the graph. So what is the output here? So that is A represents the residual voltage, and B that is the gap between 0 and B. O and B, it represents a linear voltage, and OA represents the residual voltage. See, can you spot the difference? Can you spot the phase? So flux produced is a 180-degree out of phase. One is 120-degree in phase. So we have already seen this, what is happening here. Yes. So these are the advantages of linear variable differential transformer or a transducer. So it is having a smooth and wide ranges of operation. So LVDT has a very wide range of the measurement of displacement. So it can measure displacement rate ranging from 1.25 mm to 250 mm. So it is a very high sensitivity device. So it gives a very high output value, so that there is no need for any amplifier circuit for the amplification process. Typically, the sensitivity of the LVDT is recorded as 40 volt per mm. So it is very high sensitivity. It is a device of very high sensitivity. So low hysteresis losses observed here, and no low friction losses observed here. It is of the rugged operation. It can tolerate a high degree of shock and variation, especially when the core is loaded with a spring. Okay. So direct conversion to electrical signal. They convert linear displacement, that is a horizontal position change, is being converted to its equivalent electrical quantity. It is a fast dynamic, it is having a fast dynamic response. So due to the absence of the friction, its dynamic response becomes very fast to change in the core position. Yeah. Next comes the disadvantages of LVDT. Since the LVDT is in the inductive transducer, we have already seen this in the introduction part. So it is a very sensitive to stray magnetic field. Hence, an extra setup is required to protect it from the stray magnetic field. Yeah. It is also gets affected by the vibrations and temperature variations, because it is having a very high sensitivity. Yes, that's the reason. Application of LVDT is that it has been used to measure the physical quantities as force, tension, pressure, weight, etc. These quantities are first converted into displacement by the use of the primary transducer, and then it is used to convert the displacement to the corresponding electrical equivalent. Yeah, it has been mostly used in industries as well as in the servo mechanism. It is also used in the industrial automation, aircraft, turbines, satellite, and hydraulics also. So LVDT specifications are, so it is in the first point itself we have observed no. So the range of measurement is plus or minus 0.25 mm to plus or minus 750 mm. So the operating temperature is minus 265 degree to 600 degrees Celsius. So frequency ranges is from 550 hertz, 50 hertz to 20 kilohertz. Thank you.